Hello, here we will discuss about the absorption of CSF. So basically, as I've said, after it enters during the circulation of CSF, after it enters the subarachnoid space, it is absorbed by arachnoid granulations into venous sinuses, which is basically what absorption is. By arachnoid villi or arachnoid granulations, which are basically this, found in the subarachnoid space, found protruding out from the subarachnoid space into the dural venous sinuses. We have arachnoid granulations. Basically, what happens is that the CSF is absorbed by the arachnoid villi, arachnoid granulations into the superior sagittal sinus, basically, which becomes a part of venous blood and is drained into heart. So this flow where the CSF, which was first extracted from cerebral arteries, from the blood in cerebral arteries, is passed back into venous blood to the heart. This flow is referred to as bulk flow, which is regulated by CSF pressure. The regulation of bulk flow by CSF pressure is important while talking about absorption of CSF. Let's look into it. Here, the Starling's hypothesis plays a role, so be careful when I talk about this. The colloidal osmotic pressure of plasma is 25 milligram of mercury higher than that of CSF. What does that mean? Basically, this will be the blood component, as it is the dural venous sinuses. Then you have the arachnoid space here, which has the CSF. So basically, what happens here is that the CSF here, the CSF here, then you have the dural venous sinuses here. This dural venous sinuses has a higher pressure, 25 milligram, the higher pressure than that of what is inside the subarachnoid space. So this will be the higher pressure area, this will be the lower pressure area. So according to Starling's hypothesis, fluid will have a tendency to flow from higher pressure area to lower pressure area, which will cause reabsorption, right? So what our basic aim is to get CSF from superior sagittal sinus to the subarachnoid space. So as there is already a high pressure gradient existing between these membranes, you can see, according to Starling's hypothesis, this particular reabsorption is facilitated. And another factor is the hydrostatic pressure of CSF, which is higher than that of the dural venous sinuses. CSF, which is in the subarachnoid space, will have a higher hydrostatic pressure. So since it has a higher hydrostatic pressure, this will cause a flow out. Since it has a higher hydrostatic pressure, this will also cause a flow into the cell by Starling's hypothesis. I want you to recollect that colloidal osmotic pressure and hydrostatic pressure works differently. So basically, CSF formation and absorption graphically can be represented by plotting it against the flow in millimeters per minute and the outflow pressure of CSF in millimeters of mercury. So basically, as you can see, the formation of CSF remains stable and is unaffected by the outflow pressure, but the flow of absorption up to 68 milligrams of mercury, it stays constant. But after that, when it is raised up to 112 millimeters of mercury, you can see that the absorption shorts up. This is basically the CSF formation and absorption graph, and that concludes my topic about absorption of CSF. Thank you.